Let's take a look at section 14.3, which covers partial derivatives. So a couple of learning objectives this time. That'll just be to compute partial derivatives of multivariable functions. And then we'll introduce one theorem at the end, that being Clairaut's theorem, which will relate some second order partial derivatives together. But starting with just the definition of a partial derivative, and all it says is that if we break it down to that limit definition, where we would normally take f of x plus h minus f of x over h was the Calc 1 definition of a derivative. If we're doing a partial derivative with respect to x, then we're only going to be adding h to the x term. Conversely, if we were going to be taking the partial derivative with respect to y, we'd only be adding h to the y term, which means we're only going to be focusing on one variable at a time when we're taking these partial derivatives, so either x or y. But we don't want to consider both as variables at the same time when doing partial derivatives. And also, we could extend this to x, y, and z, as we probably will. But for starters, we'll just look at 2 dimensions. So some of the notation for these partial derivatives, if we check out the lower right over here, I've written down a couple of examples. We have an adaptation of the usual sort of standard notation for a derivative, which would have normally been df over dx. But since this is a partial derivative, it changes to delta f over delta x. This symbol, the d with the little curl at the top is the Greek letter delta. And oftentimes we'll just abbreviate that to del, because we like shortening things. And so we might also call it del partial. So that's one of the standard notations. One of my favorites is the subscript notation, which is the one listed second. F sub x means f partial x. Or we could also say del partial x if we don't want to specify what function we're taking the derivative of. So if we just want to say, in general, take the partial derivative with respect to x, we could say del partial x. Or if we know we're taking the derivative of a function named f, then we can call it f partial x. And then another notation, f sub 1, just lets us sort of generalize our variables. So this is the partial derivative of f with respect to the first variable, since we don't necessarily need to use x, y, and z all the time. We could have other variable names. And in that case, f sub 1 for the first partial derivative. If we look at some more notations from out of the textbook, x is going to be that first derivative, so it gets subscript 1. Y is the second derivative, so it gets subscript 2. If we want to extend that any further beyond. Also, sometimes a large capital D is used to represent a partial derivative, where the subscript then goes on that D for deciding which variable we're taking a derivative with respect to. And then to come back to one of the points I made initially, if we're looking to find these partial derivatives, and say we want to get the partial derivative with respect to x, we're going to treat y as if it were a constant, and then just take the derivative of f with respect to x. Conversely, if we go to take the derivative of y, we pretend that x is a constant, and so that y is the only derivative we're paying attention to. Okay, so for a multivariable function that's x squared y plus sine xy, we want to find first the partial derivative with respect to x, and then second the partial derivative with respect to y. So if we were to do f partial x, so again, we're just going to be treating x as the only variable, y is going to be a constant. Out of that first term, just pretend that y is a constant, so we only really need to take the derivative of x squared, which is 2xy, plus the derivative of sine xy, which would be cosine xy, times the chain rule, the derivative of xy with respect to x is going to be just y. And that's our partial derivative with respect to x. Again, we just pretended that y was a constant. If we do the same thing, but this time get the partial derivative with respect to y. Again, I'm changing the notation for the derivative there just because the subscript one is my favorite because it requires the least amount of writing. But if we go through that again, the derivative of x squared times y should be x squared times 1. So we only need to take the derivative of the y terms. Plus the derivative of sine xy is going to be cosine of xy times the chain rule part. The derivative of xy with respect to y is just x. And those are our two partial derivatives. Notice that those two are not equal to each other. So f partial x is not equal to f partial y. And in general, those two things should come out to be different. Then if we go into second order partial derivatives, meaning we're taking two derivatives of a function f, then it works much the same way that it does from back in Calc 1. If we take two x derivatives, we call that f sub xx, meaning that we take two derivatives with respect to x. It's the second order derivative. So some of the interesting stuff is going to show up when we start taking mixed second order partial derivatives, meaning that I'll do one derivative with respect to x and another derivative with respect to y. And I just want to highlight something in the notation. So notice that for the subscript notation, if I have f sub xy, that means first take the derivative with respect to x, and then second take a derivative with respect to y. But if we convert that subscript notation to the del notation, the order reverses. At least the order in which we write stuff down reverses. So that if we're reading the delta notation, we actually read our derivatives from right to left. So that last term that I highlighted, delta squared f over delta y delta x, says first do a derivative with respect to x because it's the rightmost delta on the bottom, and then second take a derivative with respect to y. So order switches between the two notations. Order switches between subscript and del notations. So if we come down to look at all four possible examples of second order derivatives, twice with x, the two both mixed being first x then y versus first y then x, and both y derivatives, we should see that in both of the mixed second order partial derivative cases, the order between that x and y are written down changes, but the order in which they are done does not. So f sub xy versus delta y delta x both mean do x first and then y. But again, the order in which they're written down will change. And then along that last column is if our function f is z equals f of x and y, then we can just replace f with z. All right. If we take a look at some examples, we'll consider a function g this time, and it's three different terms, xy plus x sine y plus y over x. We'll find both mixed second order partial derivatives. So the first one, we're going to do x then y, and the second one, we're going to do y then x. So we'll start by finding gx, g sub x, g partial x. So we'll take each of these derivatives with respect to x. So we should get y plus sine y And then y over x is the same as y times x to the negative 1. So this will be minus y over x squared. With, of course, a 1 went here and a 1 went there, since I was taking derivatives with respect to x. If we then move on to get g sub xy, so g partial x partial y, then I'll just take the derivative of that piece with respect to y, which should give 1 plus cosine y minus 1 over x squared. 1 over x squared. And that's our first mixed second partial order derivative. If we go again, this time we're going to do y first. So g partial y, go through it this time. We should have x plus x cosine y plus 1 over x. So again, this time we just pretend that x is a constant and take all of our derivatives with respect to y. Of course, there's also a times 1 on that first term, since that derivative of xy is just x times 1 if we're taking derivatives with respect to y. And then look at the other mixed second partial order derivative, g sub yx, so g partial y partial x. And get some more derivatives here. The derivative of x is 1 plus x times cosine y is just 1 times cosine y plus the derivative of 1 over x, which is just x to the negative 1. So this will be minus 1 over x squared. And hopefully we've noticed something interesting about these two mixed second order partial derivatives, and that's that it didn't matter if I did x first and then y, or y first and then x. I ended up getting that those two were equal. In both cases, 1 plus cosine y minus 1 over x squared. And in fact, that is the theorem that we're going to look at for this section, specifically Clairaut's theorem. So this one's fancy enough to get its own name. And that says that if we have two mixed second order partial derivatives of our function f, and if they're continuous and defined about a point, then they are equal to each other. In other words, f partial xy is the same as f partial yx when f is nice enough. Most of the time, most of the functions that we're going to look at are going to be nice enough functions. So that pretty much all the time we can say that our second order partial derivatives, if they're mixed, it's the same as doing either order. But an example of when things don't work out that way would be the function listed here. Something where I've got some kind of a problem at a specific point. In this case, it's if I plug in the point 0, 0, I'm going to end up getting 0 over 0, which means that our function is not necessarily nice enough there. So Clairaut's theorem probably is going to fail on this function at the point 0, 0. But at any other point, Clairaut's theorem would be just fine.